Hi everybody, and welcome to the flipped instructional session. This is Physical Science Semester B. Today we're talking about 1.03 Simple Machines. As a reminder, be sure you take notes during the recording. You can use those notes on quizzes and unit tests, and they can also be submitted for extra credit. Make sure your notes are complete, and you do that by titling your note page with the lesson number and the title. So just a reminder, you get into the course by going into content, and then as you look down, you can see recordings, extra credit, and today we're looking at 1.3. So there are no instructions up here that I've added, but you always want to check that. So let's jump right into the lesson. All right, simple machines. Have you ever had to clear snow off a sidewalk? If so, you probably used a simple machine, a shovel, to make the task easier. People often think of simple machines as complicated devices, such as appliances, computers, and cars. In this lesson, you'll learn how machines are defined in physics, and you'll also learn about different types of simple machines and how they're used to do work. The student guide is here and available. It is always optional, nothing that needs to be submitted. And as we get into the first page, here's your first definition to write down in your notes. So in previous lessons, we learned that energy is required to do work. We know that work is applying a force to move an object over a distance. So a couple of definitions there. And then a machine is any device that makes work easier. So make sure you have that definition written down. And they make work easier by changing the strength or the direction of a force. So you also need to have this part included in your notes. So if you need to pause the recording at any time to write those things down, please do so. So important to know, machines do not decrease the amount of work that needs to be done. You still have to do the exact same amount, but they make it easier by changing the way it's done. People often think that machines must have buttons, knobs, and moving parts, but many everyday objects such as rakes, bottle openers, and ramps are machines too. So we'll look at the three images and how do they make each task easier. So if you look at the bottle opener, imagine if you did not have an opener like this and you were trying to just do it with your hand. It would take a lot more energy. Raking a yard. So how does a rake make it easier to gather the leaves up? So instead of just using our hands, we've got these fingers on the end of a stick. That definitely helps make the job easier. And how does a ramp make it easier for this woman in the wheelchair to reach the top? So normally we just see stairs going up to a door, and in her case, she's not able to walk up the stairs. So she's still, by the use of a ramp, the simple machine, able to do the exact same amount of work, which is getting in the door, but it's just easier with the ramp. All right, so if we look at the answers, just everything we talked about. And we're ready for our next slide. All right, so organizing your ideas. As we work through the lesson today, this is a graphic organizer that you can use. One graphic organizer for each of the following simple machines. So it does let you or ask you to go ahead and put each simple machine. That you do need to know all 6 of these, so I would make sure you have those in your notes. And then draw a diagram of each machine, describe how it works, and describe 3 examples where you can find it. This is optional. You don't need to do that, but it is important to understand how each machine works. So that you will want in your notes. So the graphic organizer is a great way to make sure you have everything in. So machines make work easier. A machine can change the strength or direction of a force. We know that work is equal to force times distance. So to decrease the amount of force required to do work, you can increase the distance over which the force must be applied. So think about the picture here. You're using a simple machine, rolling the box up the ramp. We've got wheels, we've got a ramp, so that makes it much easier than lifting this heavy box onto the back of the truck. So suppose your family is moving. The work required to put a box on a moving truck is 1,200 joules. The distance from the ground to the back of the truck is 1.5 meters. If you tried to lift the box from the ground up onto the truck, you would have to apply a force of 800 newtons. Okay, so we can see that work, you've got 800 newtons times 1.5 meters gives you joules, right? 1,200 joules. So now suppose you use a ramp that is 6 meters long to load the box on the truck. Using the ramp, you only have to apply a force of 200 newtons to load the box, even though you have to move it over a longer distance. So if you apply a force of 200 to move an object 6 meters, how much work is done? So if we look, 200 times 6, it's still 1,200 joules. So it's the same amount of work that's done without using the ramp, but less force and more distance are needed. Okay, remember that joules, right? We talked about joules, it's energy. It's how we measure energy. So you use the letter J, it's a capital J. So don't forget that unit. Okay, what a predicament. This man told his friend that he could move a heavy rock by himself in his backyard. The rock is too heavy to lift by hand, and he does not want to ask for help, so he's using a machine. It's a crowbar, and he's going to try to pry the rock off the ground. So in this case, the machine changes the direction of a force to make work easier. So a simple machine, remember, it's a machine that makes work easier when a single force is applied. Make sure you have that definition. Simple machines cannot do work by themselves. You must provide the energy to make a simple machine do work. For example, when this man does work on the crowbar, that means he's applying force. The crowbar does the work on the rock. So a crowbar is a type of lever. So you may want to make that connection in your notes. And a lever is one of the 6 types of simple machines. Looks like it skipped a page. Okay, so input and output force. These are important words you need to know. When you use a simple machine, you apply a force. The force is called input force. So the work we are putting in is input. The force that the simple machine applies to an object is called the output force. So you can look at this picture and see the man putting in force, and the box is going to be lifted, and that is going to be the output force from the lever. So use the animation to see the input force acting on the simple machine. And when an input force is applied to one end of the board, the output force on the other end of the board lifts the box. So the machine magnifies the input force so that the resulting output force is greater. However, the work you apply to a simple machine is always equal to the work the simple machine applies on an object. Notice that the man has to apply his force for a distance greater than the height in the box, then the box is lifted. So here's a summary of what happens in this scenario. So the man exerts a smaller force over a greater distance. The box experiences a larger force over a smaller distance. And as a result, the work done is the same. Okay, so we're watching it again. Input force is what's going down. Output force, the box goes up. So input or output force. It is important to be able to label these and know which is which. So the purpose of a simple machine is to make work easier. In many cases, the purpose of the simple machine is to decrease the amount of force needed to complete a task. Have you ever tried turning a screw or a bolt with your fingers? It hurts, and it often doesn't work too well, if at all. So use the table to help distinguish between input and output forces. Remember that the purpose of the machine is to it's going to magnify the input force, creating a greater output force. So here we've already done this example on the previous page. So the man is the input force and the seesaw is the output force. Here the person shoveling is the input force and the output force would be the shovel moving the snow. Okay, here you've got a person with a wrench. You've got the hand on the wrench. That person's hand is doing the input force. The part of the wrench here is the output force to the nuts and bolts. So let's talk about levers. You do want to have some notes about levers. It's a simple machine that consists of a rigid bar that that pivots on a fixed point called the fulcrum. So you need to know the fulcrum as well. You need to know the definition. Levers can change the direction of a force. This seesaw is a lever. It changes the direction of a downward input force, right? So pushing down to an upward output force. Levers can also change the strength of a force. So look at the second image. If you tried to remove a cap from a bottle with only your hands, you would have to apply a large force over a short distance. However, if you use a bottle opener as a lever, you can do the same work over a longer distance with less force. The fulcrum of the bottle opener is the point where it rests on the bottle while lifting the cap. Other examples of levers include a shovel, crowbar, and a rake. Can you name more? So if you are filling in the pages of the graphic organizer, which I do recommend, you've got 3 examples right here. If you're not and you're just putting these things in your notes, you do want to put information about where you find the fulcrum. It did say it's where it makes contact with the object. So the fulcrum of the bottle opener is where it rests on the bottle. And then your examples, make sure you have the definition of fulcrum. It's the fixed point. Okay, and make sure you know what a lever is. Make sure you have that definition. Okay, so we see a jack, like for taking off a tire. We see a seesaw, those examples as well. All right, inclined plane. It's a flat slanted surface that's often used to lift things. So most of the time we think of an inclined plane being a ramp. It also changes the strength of a force. A ramp is an example of an inclined plane. Think back to the example of the ramp and the moving truck. The ramp reduced the amount of force needed to lift the box by moving it over a greater distance. So the longer an inclined plane, the less force is required to move an object upward. So look at the image of the wheelchair on the ramp. With a longer ramp, the distance to the bus would be longer because the ramp would extend out further into the road. However, a longer ramp would require less force for the wheelchair to reach the top. So make sure you have the definition of inclined plane, flat slanted surface. Okay, a screw is another type of simple machine. It is an inclined plane, and you can see the picture, how it looks like a swirling ramp, and it's wrapped around a post. So the inclined plane makes up the threads of the screw. So imagine that you could unwind the threads of a screw. The closer together the threads are, the longer the inclined plane, and the smaller input force is required to get the same output force. All right, so think about that. Look at the picture, kind of process. It's a lot to put in your mind there, but you've got this picture of a screw. You've got a rotational force, okay? As it rotates using the threads, okay, which is the inclined plane part, you've got this linear force that's driving it down. So the screw converts that rotational force into a linear force, okay? And it's by the shape and the angle of the inclined plane on the post. So a screw is a simple machine that changes the direction of a force. So can you see how the directions changed from rotating to linear? When you turn a screw into a piece of wood, you apply a twisting force. The screw changes the direction of this force and moves in a straight line into the piece of wood. So it's converting rotational force to linear force. And you may want to put that in your notes. All right, a wedge. A wedge is a two-sided inclined plane that can be used to separate materials. So in your notes, I would definitely put an axe as an example, and make sure you have the definition of a wedge. This axe is an example of a wedge, and so as with a screw, the wedge changes the direction of a force. So when you use an axe to split a log, your downward input force is changed into a sideways output force. So if we look at the picture, the blade goes down and the force now moves out. Okay, so it changes the downward input force to a sideways. As with all inclined planes, the wedges that are long require less input force for the same output force. So other examples of a wedge include knives, chisels, and your teeth. So those are great examples to write down as well. Think about scissors, any kind of sharp object that cuts. All of those would be great examples to include. A wheel and axle, this one is pretty easy. It's a simple machine composed of two attached circular objects that rotate in the same direction. The larger object, which is the outside, is the wheel, and the smaller object, the inside, is the axle. A Ferris wheel and an electric fan are examples of wheels and axles. With these simple machines, the input force acts on the axle, and the output force is exerted by the wheel. Okay, so think about that. Make sure you maybe draw a picture and label it. Input force is on the axle. A steering wheel and a doorknob are other common examples of wheels and axles. And when you use these simple machines, however, you apply an input force to the wheel and the axle exerts the output force. So depending on what you're doing and what type of wheel and axle we're looking at, where the input force and output force can change. So that might be something to note as well. So when you use a doorknob, you apply a force to turn the wheel of the knob. The axle of the knob applies the force to open the door latch. A pulley. Okay, a pulley is a simple machine that consists of a grooved wheel that holds a rope or a cable, as shown in the first image. Pulleys are often used to help lift objects. The student in the second image is using a fixed pulley to raise a flag on a pole. When the flag is attached to one end of the rope, the input force is applied to the other end of the rope, and the flag moves upward. So that might be something helpful to draw in your notes, especially where the input force and output force is applied. I would definitely have that in your notes. And in this example, the pulley changes direction of the input force. So when we're looking at the flagpole, the pulley is changing the direction of the input force. The input force is exerted downward on the rope, but the output force of the rope is exerted upward to raise the flag. In this case, the pulley just changes the direction of the force, not the magnitude. Lifting heavy objects can be quite an endeavor. If more than one pulley is set up, then less force is needed to lift the object. Pulleys reduce the force needed to lift the load as it's moved over a longer distance. This type of moving pulley is often used to load cargo onto boats and is shown in the third image. All right, so we've got a clothesline, and that's a first example. Then we've got the flagpole going up, and finally we've got the pulley moving the freight onto the ship. All right, so the big ideas. This is something you might want to do as you're kind of gathering your thoughts at the end of the lesson. Simple machines are frequently thought of as tools. So which tools belong in which category? So you can test your knowledge, how well you understood this, by going and moving the items as they come. Elevators go on a pulley. So just checking and seeing how well you understand and if you can place all of those in the correct spot. So one thing you need to have in your notes too is the word mechanical advantage. Have you ever wondered how you're able to lift an incredibly large object like a car with a very small device that fits in the back of the trunk? A car jack is a device that makes such a feat possible with very little effort. Lifting a car requires a very large force. The jack makes it possible to take very small input force and produce a much larger output force. This is referred to as mechanical advantage. Okay, so taking a small input force and producing a large output force, that's what mechanical advantage is. And it's calculated by taking the ratio between the output force produced by the machine and the input force produced by the user. So write this formula down so that you could calculate it if you needed to. And then that gives you a problem that you can work through here. What's the mechanical advantage of a car jack if the input force is 25 pounds and the output force is 2,000 pounds? So we would need to divide 2,000 by 25, and that gives us an answer of 80. All right, going into the last slide on this one, mechanical efficiency. A lot of people assume that because a simple machine like a car jack makes a process easier, you are getting something for free. The way a car jack and other simple machines work is by taking a large amount of work and spreading it out over a longer distance and time. So in doing so, the force required to lift something is much less. However, there is usually more friction along the way, and in the end, the process takes even more work. This is where mechanical efficiency is determined. Mechanical efficiency is the ratio of work produced by the machine to the work put in. So make sure you have this formula as well. Efficiency is equal to work out divided by the work in. So what's the efficiency of a lever that requires 2,500 joules of energy but produces 1,500 joules of energy? So it requires, that would be the work in, produces, that would be the work out. So our answer would be 1,500 divided by 2,500, and that is 0.6. All right, let's review really quickly. Definitely, I encourage you to go through and make sure that you have these words defined. Putting them into here is good practice to make sure you understand them. And then as we wrap up, we learned about the different types of simple machines and explained how a simple machine is used to make work easier. So answering the following questions: how can a simple machine reduce the amount of work needed to lift an object? I encourage you to put these in your notes. You often find these as quiz questions. So the answer here is by increasing the distance, the input force can be reduced. Okay, so that's question one. And second, how can an inclined plane make work easier if you have to move a load over a longer distance than if you lifted it straight up? And we remember that moving example because the work involved in lifting the object remains the same. So lifting it straight up might be less distance, but it requires a greater force. So when you use an inclined plane, the distance increases and the force you need to apply decreases. All right, so that takes us to the end of the lesson. We've gone through everything here. As we wrap up, the next steps, just look for your next flip follow-up session. If you need help with any content we talked about today, please come see me in Help Lab. Have a great day.